welcome everybody to a joint EECS robotics seminar featuring Marc Miskin from the University of Pennsylvania. Marc is an assistant professor of electrical and systems engineering. He received his bachelor's of physics at RPI and his PhD in the same from the University of Chicago. He was also a Kavli postdoctoral fellow for nanoscale science at Cornell. He is interested in the design and fabrication of microscopic robots, and his work has won awards from the Air Force Office of Scientific Research, the Army Research Office. He's won a Sloan Research Fellowship, a Packard Fellowship, and he's been featured in several interesting popular media outlets, including the New York Times, MIT Tech Review's 35 Under 35 list, CNN, BBC, NPR, etc. Aside research, he's actively involved in science education. He has an exhibit in a museum, he was telling me, like an espionage type of spy-like thing.
No, it is literally the science of it's all the James Bond movie props and then real-world versions of it. And we are the evil nanovirus. I'm the bad guy.
He's the bad guy, right? But I can tell you...
Which these days is not necessarily a bad thing. You be honest.
Well, on that note, I guess, right? Well, let's put an applause together for our speaker, Marc Miskin.
So thank you. I wanted to say I've had an absolutely fantastic time visiting here. I didn't realize, but I feel like Michigan is in many ways sort of the spiritual foundation of the work that we do, because it's a hub for robotics and it's a hub for small computers. And it's been super cool to come to a place where not only does everyone seem to work on the things that I think are really cool, but also with somebody who has 2 M's in their name, to see M's everywhere that I go, I feel very welcomed. And so I've been having a great time. So I want to tell you about our work today in making very small robots. And when I say small and when I say robots, I really do mean both things. So to orient you for the sense of kind of what you're going to be looking at the talk, these are 2 of our robots right here and here, and we've placed them on a microscope slide that we took from a high school biology kit of a slice of skin tissue. And so you can see these are kind of like hair follicles growing out. This is the top layer of the skin, the part that you shed off. And these are our little tiny robots at about 300 microns on the side. These robots were built actually with David here, who's in the audience, and they are robots in every sense of the word. They have onboard sensing, they have onboard computing, they have memory, and they can move around. And so that's really the story I want to tell, is how do we get all of the features we typically associate with robots on the robot, but keep it in a size that is under 1 millimeter. That's just about too small to see. And so that's the pitch of our story, and that's what our group does. And so to motivate that, I like to start a lot of my talks with this video. I've been showing this video for 6 years. I still have not gotten tired of it, which is, I think, a testament to just how cool it is, of why would anyone want to do that? And for us, sort of the inspiration in some senses, because it's there, because you can do it, because nature shows you that it's something that's real and it's something that's important. So this is a microorganism. This is probably my favorite microorganism. It's called a rotifer. And these things live everywhere on Earth. They live in saltwater, freshwater, and they live in creeks in New Jersey, where I grew up. And when I was a kid, I was in this after-school program where we took pond water out of this creek, we put it under a microscope, and I saw this thing hanging out underneath, doing what it's doing now, which is eating. So this little rotifer has a bunch of little hairs on its face called cilia that it moves around quickly to suck up, in this case, this bacteria that it wants to consume. And this thing totally blew me away. I thought this was the coolest thing ever, right? That naively you would imagine that something that's small would have to be boring or dumb or not capable. And nature shows you that that's just completely wrong, right? This is an animal doing a complex task. It's hunting, it's seeking down food. It's carrying out that task by going through a sequence of operations, by moving around. And it's fully autonomous. Obviously, it's an animal. Nobody tells it what to do. And its whole universe fits in a drop of pond water. And I think that's an enormously fascinating idea as a scientist. I also think, because this is sort of a fundamental length of biology, it's an enormously important idea as an engineer. And so kind of the quest of our group is, how do we one day, 50 years in the future, build something like this, right? Something that is too small to see by eye, but still possesses the things that we would normally associate with robots. And if this is what you want to build, I mean, you don't want to build exactly a rotifer, that would be super hard, but like something that approaches a rotifer, you got to do 2 things at once, right? One is you got to figure out how to make something that's small and smart, something that has sensing, computing, mechanisms of information processing on it. It's not enough just to swim around. You got to go find your food and eat it. And the other is you have to tie that to some system for control, for motion, right? To have it be a robot. It has to sense, think, and act. That's what it needs to do. I'm going to split the tasks into these two parts and say, suppose we could chunk these up as being having to build information systems, and we could chunk this up as being mechanical systems. And so in some sense, the challenge here is how do you build all of these and then integrate them together into one simple part? And I'm going to chunk them up this way because it allows us to look at what people currently do in the literature and say, like, well, how far off are we from building something like this? So first, we'll look at how do you build something that's small and smart? Like, what have people built? And there's lots of reasons for hope here. And then we'll look at what people have done to make something move. Lots of reasons for hope here, too. And then we'll really see what the challenge fundamentally is. I'll skip to the punchline since I'm at and you guys have been making tiny computers now for like 30 years, is it? Like when was the first micro mode? It's pretty awesome, yeah. But today, you know, thanks to people like David and the group here, the tiniest computer in the world is remarkably small. And so probably a lot of people here are familiar with this image of the world's smallest computer, which is still a record that you guys hold, sitting right here next to a grain of rice. And so this is a full computing system. It's got a processor, it has memory, it has power on board in the form of little solar cells. It's even got a little LED on it for blinking data back out. And all of this fits inside of a space that's under 300 microns on the side, right? This is an extremely tiny space. And so if you're a roboticist, this is noteworthy, right? These are all the parts you would want for a robot: a sensor, a processor, memory, power, and communication. And all of this in a space that's actually not much bigger than that rotifer, right? The rotifer is 70 microns, this thing's 300 microns. You're getting close. This is sort of a logical continuity of trends, and I figure I'm going to again steal from David, of sort of a progressive reduction of computing sizes since the 1960s. So this is a fancy name of Bell's law, but it's basically the statement that if you plot the volume of various computing systems since the 60s, you get this nice power law of decreasing sizes, which has held up remarkably well to the point where if you were to extrapolate it out, you'd look and say, okay, we should be hitting under sub-millimeter in 2020, and lo and behold, devices like this start showing up. So the main message is that this trend has been remarkably durable, and it's put us into a regime where we can now legitimately build computing systems under a millimeter in a size, and that should make us very optimistic that there's really a path to building a very, very small, very, very smart robot. The other half of building kind of the systems for moving around has been equally active, but extremely diverse, right? So if you were to go into Google and type microrobots, or like in Google Images, you'll probably get images that look like this. So these are various examples I pulled down from Metin City's group making acoustic propulsion systems, Sui Gao at Caltech making, you know, bubble rockets, so like little chemical reactions that shoot out behind basically a rod that then moves it around through space. Brad Nelson making kind of magnetic corkscrews, so little twisty skews with magnets on the top that you can then rotate the magnet and propel yourself. David Gracias's group at Johns Hopkins making little magnets with grippers on them. All of these are different mechanisms of moving around. They're all definitely micro, right? The scale bar here is like 10 microns. But in some sense, they're not quite like robots in the way that we would normally think about them, because really all of these things directly convert one form of energy immediately into another. So acoustic into mechanical, chemical into mechanical, magnetic into mechanical, with nothing in between, right? There's no way of modulating this process to control where this thing goes. So in my view, these are really amazing, and there's this huge diversity of different ways of propelling at these small size scales. But there's a challenge, which is that they don't really have a clear path for integrating with those systems for information processing. And so the story I really want to tell today is this, is that if you were to look at what people have been doing sort of in these spaces for like at least the last 5 to 10 years, you could kind of say the following, that there's loads of ways of making small bodies, things that move around at tiny length scales. There's a very powerful platform for building brains, so systems for information processing. But how do you do both at the same time? Or like, how do you build in a single robot the capability for information processing that also integrates with mechanical control and do it without going over a millimeter, right? With staying on these very, very small dimensions. And so that's the crux of almost all the stories I'm going to tell you today, is sort of where we've put a lot of our research effort in addressing this, in either building new actuation systems that play nice with silicon, or building new information processing approaches that can integrate with these on the other side. And so our first success story that kind of gave us hope that this is going to work happened in my postdoc at Cornell. So I'll share with you briefly kind of how we approached this and what we did. And what we realized kind of early on was that the big challenge here is if you were to look at all of the actuators that existed, and you were to look at the size they can operate at and the voltage that they require, they're incompatible. That there was no existing actuator that operates at a low enough voltage to play nice with semiconductor electronics that also works at a sub-millimeter scale. And so we spent a lot of time developing it, but ultimately we came up with this. which we called a surface electrochemical actuator. So this was our first sort of attempt at building something that could be a microrobot. So what you're looking at here is this is the actuator. It's a bending actuator, and right now it's curling up into like a little curlicue shape. And you can see when you dial the voltage back down the other side, it unfurls into this kind of more straight shape. It's moving kind of erratically. Oh, by the way, the voltage is being supplied by this big metal rod on the side, and we're just biasing it through that rod relative to water that it lives in. Now, the biasing is kind of erratic in this video because I'm super excited. I've just gotten this thing to work for the first time, and we're like dialing the knob up and down. We're like, look, it's alive, it's doing stuff. And we're excited because of the scale bar, which is in the bottom corner at about 4 microns. So if you were to put a red blood cell up on the screen, it would be about yay big relative to this actuator. This is an unbelievably tiny actuator. And the other reason we're excited is because we know the voltage range we're using, and it's about 200 millivolts, right in the sweet spot of what you'd want for semiconductor electronics. So how does this thing work? Well, what you were looking at was an extremely thin layer of platinum capped with a layer of titanium. And so here's a cross-section of one of these devices that we cut out while we were fabricating it to show what it was made of. So here's the silicon wafer we built on. We put a little layer of aluminum in between it so we can peel these things off and play with them like you saw in the movie with the probe tip. And then there's a thin layer of about 10 nanometers or so of platinum with a thin layer of about 2 nanometers of titanium on top. So just a couple dozen atoms worth of material in the full cross-section of the actuator. Now, how does it work? Well, it turns out that if you take platinum and you put it in water and you put a voltage on it, atoms from the water will attach or remove themselves to the surface of the platinum depending on how much voltage you use. When you do that, you create a difference in the surface stress on that layer, and that surface stress leads to bending. Basically, before you didn't have atoms, now you do have atoms. There's an additional energy associated with that that creates a force. Now, what's nice about that process is because it's fundamentally electrochemical, it's both reversible and operates at a very specific voltage range of about 200 MV. So if you take your actuator and you say, drive it to very low voltages, like when it was basically unfurled in that movie, you're stripping off all of the atoms adsorbed to the surface. If you drive it all the way forward, it saturates when you filled up every site on the surface. And in between, you have a nice logistic function that goes from one side to the other with a span of about 200 millivolts from end to end. Exactly what you'd want to play nice with semiconductor systems. We did some more characterization for this thing. It actually turns out it's a very good actuator for microrobotics. If you look at the force, you get about 1 nanonewton of force, which for big robot people is probably frightening, but for us is enormous, right? So if you're a 50 micron robot, you can carry about 100 times your body weight. You're basically like an ant because you weigh nothing because you have no mass. So a nanonewton is huge. And likewise, the power consumption is on the order of about 1 to 10 nanowatts. It's basically set by background electrochemistry on the platinum, which again is a very, very tiny power. As we'll see, we typically can build things that run at about 100 times more in both their power transfer and in terms of the power requirements for information processing. So everything you would hope for, right? Low voltage, low power, high force, small size, all very good. There's one last key property about these actuators, which is why we love them so dearly. Which is because they're made of platinum, they're made with a standard cleanroom compatible material, and the processes we use them are processes that are commonly used in semiconductor processing. And so just like circuits, you can also build 1 billion of them, right? So you don't just have to build one little tiny actuator, you can make 1 million little tiny actuators. So here they've all been wired to a common voltage node, we're driving them all together, and they're waving at you looking like the legs of your future robot army. This is really great when you've had a bad day as a postdoc and your paper's just been rejected and you can feed your God complex by watching your robots bow down. And then you realize that you're in a basement in Ithaca all alone watching robots bow down in a petri dish. You wonder, what am I doing with my life? But anyway, I overcame that and we were super excited about this. And so we said, this is awesome, let's try and build a robot. And so the first robot we built was really simple, about the dumbest proof of concept you could come up with just to make the design simple. It basically consisted of the most idiot version of electronics we could build, so just 2 solar cells, power essentially, wired directly to the legs. And to go from that weird like bending structure to something that looks more like a robot, we did something very simple, which is we glued big rigid panels of polymer on top so that now you can only bend at these hinges and then form legs, sort of like an origami type structure. The idea here is that if I shoot light at one of the 2 solar cells, I could drive different pairs of the legs and I can make this thing scurry around under control. The point, though, is that if you get this to work, then you've successfully shown an integration between electronics and actuation, and we'll see where that goes. Now, the circuits, obviously, we can build massively in parallel. The legs I've just shown you, we can build massively in parallel. And so that means you can now build robots massively in parallel, which I still think is super, super cool. So typically in our group, we build things on 4-inch wafers or on little chips. I like 4-inch wafers. My grad students like chips. I don't know why. But a wafer holds about 10 to the 6 robots on it. It's lithographic, so you can make every single robot different. You can make every robot the same. Complexity is essentially free in this process. So in this version, we made like 4 different types of robots. You could see each of the different columns, different bodies, but we could have just as easily made a million different robots. It would have been the same relative level of processing difficulty. The last challenge we had to figure out in building these is that these robots, this was a chip, this would be the end of the line. You build it, you're done, you put wire bonds on it, but robots need to move around. And as you can see in this picture, these are not moving around, right? They're still glued down on their surface. And so the last thing we had to figure out was how do you actually get them off of this and out into the real world? I don't want to bore you with the details because it's a very long, boring process that just features lots of different chemicals and flipping things over and weird tricks. So I'll show you the last step, even though this costs me like 3 months of my life, which is the final phase of dissolving out the surface underneath these robots. So here we're using a base to basically dissolve away a polymer underneath these robots. You can see when it dissolves, the legs snap up into their little origami structure. And now you have your army of little tiny micro robots ready to go off and do your bidding. One thing that's super cool is we actually have gotten quite good at this. So in this video, we got about 90% yield. We now have pushed that up to almost like 95, 99 in some of our more mature versions of robot release. And our less mature ones, like you'll see later, it's about 50%. But in any case, if you're making like 10 to the 5 robots and you're hitting about 90% release, it's pretty sweet. You have a swarm of like 10,000 robots and 100,000 robots, and you can do some very interesting things. All right, so last bit is, of course, to show you that these things work. And of course they do, otherwise I wouldn't be here. But let me show you that. So here's one of our little robots. And if you look very closely at the top of it, you'll see this little white dot. That's a laser that we can control and put wherever we want just by using scanning mirrors to place it. And I'm going to cycle that laser back and forth between the top and the bottom of the robot. And off it goes, marching around under my command, I guess, telling it what to do. I got very excited in doing this project. We spent like weeks just zapping lasers at little micro robots. I think that's probably still the coolest job in the world that you can have, is to get up every day and sit under a microscope and zap little robots with lasers. Like what more could you ask for in life? And we characterized actually quite a lot of this. So we wound up writing a paper later about like how these things actually locomote, the mechanisms that they produce in order for moving. And what's also sort of remarkable about this family is you'll see in a second, this robot is going to keep marching, and then you'll see this gray zone at the end, which is coming up. Keep going, little guy. Right about there. That's the end of the microscope field of view. So we've marched them basically to the ends of their earth. We have yet to establish an upper bound on the actual actuator. What typically kills the devices is the students. Either somebody hurts it accidentally or bacteria colonize the cell and then can murder the robot if you haven't built it correctly. But it's from a mechanical point of view, it's actually quite fascinating that little actuator is happy to do. We've established like over 100,000 cycles, and it still performs about as well as it did when you started. All right, so this is where I sort of left things when then I became a PI. And immediately what we decided we had to do was get rid of this laser, right? That in some sense, this is moving towards the goal of a smart robot, but it's not really a smart robot because there's still a user telling it what to do. It's not processing any information. It's not doing any computing. It's not doing anything like that. And so very quickly, maybe like 3 years afterwards, this fantastic postdoc, Michael Reynolds, who worked both at Cornell and then in my group at Penn, developed sort of the next generation of these robots that we called clockbots, which were robots that had their own internal systems for generating their gait patterns and generating their motion. And so Michael made a very simple circuit, which was basically a clock with different phase delays that you could access. And then by tying different actuators to different parts of those phase delays, you could produce different gait patterns. So we explored a couple different body types in this family. He made little quadrupeds. So here's one of his quadruped robots doing kind of a not so good turn because 2 of its legs are busted. He built bipeds. So if you're into sort of low Reynolds number robots, this is a very classic propulsion strategy called the Purcell gait, where you sort of move your front and back legs in and out of phase. And again, this robot is doing this all on its own. And he also made my favorite robot, which is this guy, which we affectionately call Antbot, which is a hexapodal robot that does alternating tripod gait. And again, this robot, no one is telling it what to do. It has its own onboard clock. It wakes up once you turn power on it. The power clicks on, it drives the legs all by itself. In some sense, it's getting us closer, right? It's definitely doing onboard generation of these signals. It doesn't have any human in the loop telling it what to do. On the other hand, we're still not quite at the level of information processing because it's just generating clocks. It's a wind-up toy, right? It doesn't really know how to move and move around dynamically. And so this was sort of our first success story. And then we got really into this, right? We said, this is the coolest thing ever. We want to build microrobots all day long and go and figure out what we can do with electronics. And so in the time since we developed these systems, my group has been exploring what we call sort of the world of electronically integrated microrobots. And broadly, the kinds of work that we do fall into sort of these 4 different buckets, right? So taking the little sensors and actuators that we develop for the robots and using them in various different applications. So you have this very cool low power actuator. What else could you use it for? Making other microrobots electronic. So legged robots are one type, but there's all kinds of other ways you can move. How do you bring them under the umbrella of electronic control? Making them smarter, and then taking the fantastic voyage, which is our broad term for saying, it'd be really cool if you could miniaturize yourself. The laws of physics say you can't, so why don't you build a robot that can go down and do tasks for you at very, very small sizes? So with the rest of the talk, I'm going to tell you about these 3 stories. So could we make other microrobot platforms electronic? How do we make them smarter? And then what are we going to do with them? What are they for out in the real world? So I'll start with this guy here. So when I came to Penn, I was offered to teach a graduate class to train up my graduate students, like many faculty students do, and I created a course on microrobots, right, which was a plan. But when you create a faculty course of your own, you have to say nice things about everybody else, right? So you can't teach a class where you're saying, I alone make the best microrobots and everybody else's stuff is bad, right? You have to present other people's work and say like what's positive about it, or there's no point in teaching that class. And so I got really deep in all these, and I started looking into like what all these things do. And I walked away with this feeling that like, these are actually really cool platforms in their own right. They have a lot of really interesting properties that you would love to be able to duplicate. The only problem is you have to figure out a way of putting something in between that transfer of energy, right? Like these robots are super fast. They're some of the fastest microrobots anyone's built. They go at like 10 body lengths per second, and they're powered by ultrasound, right? It's kind of neat. You could envision all kinds of other applications. Or like magnetic fields driving robots sounds pretty good. Like you could power them deep in the body, but like, how do we build stuff to actually make these smart? Like, is there a way we can interrupt that flow of energy and put some kind of electronics in the middle to regulate it? And so this is a trend that my group personally has gotten super into. We're trying to take as many of these as we can and convert them into electronically integrated versions, basically envisioning these systems as motors and then figuring out how to put controls on top of it. And the first class we've had success with is taking ideas from sort of electrokinetically propelled microrobots or electrophoretic microrobots and building them into now electronically integrated versions. So 2 of my students who worked on this are up at the top. This was largely by Will Reinhardt and Lucas Hansen. And they came up with a very simple idea, which is they said, okay, if you look at how electrophoretic robots move, it's actually a pretty simple idea, is you take a particle, you put an electric field around it, and mobile ions in the water around the object will move in response to that field, and that can create a flow, right? And typically, like if you think electrophoresis, you get a flow that's proportional to the electric field. But there's no rule in here that says where that electric field has to come from. It doesn't have to come from something external. It could come from the object that's moving itself. And so, he got a very dumb idea, which is, let's just rip the legs off and see what it does, right? Take one of those robots, take the solar cells, just put 2 electrodes on the front and the back and shine it with light. In principle, that should make a field. The field should make a flow and the thing should move. And lo and behold, it does, right? So we took a simple device, again, with little solar cells. We put electrodes on the front and the back. You put it into water, you shine enough light at it, and lo and behold, off it goes moving around. By the way, it's about 1 sun. It's not like a crazy amount of light. It's a fairly reasonable amount. We did characterization of this device, and you find indeed it does pretty much what you'd expect for electrophoresis. You get a speed that basically goes in proportional to the field you're applying, a speed that's inversely proportional to the conductivity. So basically proportional to current, inversely proportional to conductivity. That means proportional to electric field. And if you replot your data where you just plot speed versus electric field, you get nice data collapse between independently varying the 2 experimental parameters. Now, what's cool about this and different than other microrobots that do electrophoretic propulsion is that typically these systems generate their self-propulsive fields through chemical reactions. And that's problematic because you're strongly coupled to your chemical environment. You can't really, if the thing you're using as fuel goes away, you die. But if you're regulating this thing directly with electronics, you can compensate for that effect by just dialing up the current that you're throttling back out. And so what Lucas and Will found, which is kind of cool, is you could change the chemical environment enormously. You could put it in peroxide, you can put it in formaldehyde. Formaldehyde, by the way, should kill other self-propelled electrophoretic robots, doesn't kill this one. You could put it in straight up the eye with nothing else in it. And the only thing that happens is you slightly change the slope of that proportionality constant between field and propulsive speed. And the reason is really simple, is that whereas traditionally you generate this by external mechanisms, here we're directly regulating the flow of current with electronics. We're galvanostating it. And so we alone set the field, and we therefore alone choose the speed of propulsion. So just that one simple change, you automatically produce a lot of robustness in how this robot moves. We did a lot of studies on how these things actually function, and we did do some fluid dynamics to describe the mechanics of this process. Basically, what we found is that in that movie, when you're watching this thing scoot around, what it's actually doing is gliding on a thin layer of fluid underneath it. It's kind of almost like a self-creating air hockey table, and it was a fun little fluid dynamics problem if somebody wants to ask me about it later. But we did build a model for this where we can predict all of the parameters of what this robot does, specifically the gap it makes with the surface, the angle of attack, and its velocity, all as a function of the field strength. And we fit something like 96 data points with 3 parameters. So we're fairly confident that this model is right. But if you're into it, you can ask me. Okay, so where else can you go with this? Well, Will had a very quick realization afterwards, which is if you have a device where the speed is proportional to the current that you're applying, then what happens if you tie 2 of them together, right? In principle, if you glue the 2 sides together, then you could directly control the velocity of, say, each half of this robot by simply modulating the amount of current that you apply. And naively, you would think, this should be like a wheeled robot, right? If I have 2 wheels and I can independently control their velocities, then it's almost exactly the same as this scenario here. And so if I give this a higher velocity than that one, I would expect this thing to turn with a rate proportional to the difference in their speeds, or in this case, a difference in the illumination intensities. So what you would expect from kind of robotics 101 is you'd get a rate of rotation proportional to the difference in currents that you apply between the 2 sides of this robot. And indeed, if you make a bunch of measurements, you find out that's exactly what it does. And that means that you can then steal all of your favorite control laws from robotics to now pilot this thing around. So Will quickly began rating, elementary robotics textbooks for, differential drive control laws and then applying them to this robot by just modulating the optical power delivered to each of these different sets to, say, guide robots to specific waypoints or make them fly around in little formations like they're the Blue Angels or something like that. Again, I feel this is getting into God complex territory where, your graduate student is piloting these things around from one place to another. I'll give one quick teaser. So Will also did something else which just came out recently and we think is super cool. He also examined what happens if you take this robot and you put it in a statically patterned field of light instead of one that you're dynamically changing to pilot the thing around. So for example, this movie on the left where you put it in some weird light gradient and you let it move around. We actually worked out the kinematics for this system in the limit that the robot is small compared to the gradient of light. And you get these 2 sets of equations that are down at the bottom. One basically says that your body speed moves in proportion to the average intensity at your center, and the other says your acceleration is proportional to the gradient orthogonal to your axis in some sense. It turns out these are the exact same equations that govern what light rays do when they move through complex media, which we thought was pretty cool. It's in a very obtuse form. If you want to, you can read our preprint called Artificial Spacetimes. And from that, we're able to steal a lot of techniques from optics to repurpose them as reactive control schemes for robotics. So these are 3 robots. I'll just show you the trajectories traversing a maze that we made up artificially. So there's no real maze. We just did it. Like we said, you can't go across these lines. And we rationally constructed, or we computed the intensity pattern that would guide all of these robots to this target location on the other side. In fact, the pattern is such that as long as no robot is initially facing the wall, it is guaranteed to reach the target location in a finite time. So this was a kind of fun piece of work that we did. If you're into reactive control, we thought this was pretty neat, and I'm happy to talk with you about it later. But there's a big issue, of course, with this, which is reactive control is not where we want to go, right? Reactive control is still no information processing on the robot. And I promised you this, right? I said that I was going to do this. And so, of course, this is the part in the talk where we have to leave behind Will's fun little robots and talk about how do we make these things actually smart, right? Like, how do we go? It's cool to have things that move around under reactive control. It's cool to have things that onboard clock generation, but those still haven't delivered on this goal of having onboard sensing, acting, feedback, right? How do we get this computer to live on this device? And so when I started out, I think in 2019, I met David at, was it DARPA thing? At a DARPA thing. You know, I showed her the tiny robots, she showed me the tiny computer, we're like, we should do something together, and then immediately COVID. And so it's been quite a ride, but we did get there. And so this is the system that David's group built largely through the efforts of this graduate student, Jung Ho, who's down here in the corner. This is the robot that our group now affectionately refers to as SmartBot, which is kind of a joke. What's that?
When Jung Ho was still younger.
Yes. You need to update your LinkedIn, Jung Ho. Okay, so this robot is still very tiny. It's 210 by 335 microns on the side, but David was able to pack an enormous amount of stuff in here. So again, this robot is powered entirely by solar cells. It's very cool. It has a metabolism of about 100 nanowatts, which means it's comparable to a paramecium when the paramecium is angry and really swimming, but still kind of neat to be in the same power scale as a paramecium. It's got a set of sensors now, so it has 2 thermometers, one on either side. It also has voltmeters, although we haven't yet actually gotten those to work. We're still testing those. It has a special solar cell on the bottom, which is its communication unit. And so you can send instructions to SmartBot to tell it what you want it to do. Essentially, you modulate the optical intensity. It looks for fluctuations in intensity as bits that it should decode and then stores them into its memory. So you can write programs to this machine. It has a set of electrodes that are at the bottom, and these can be used both for the electrokinetic propulsion I just showed you and for the legged locomotion. The legged one just came online, so I'm mostly going to talk about the electrokinetic, but it is designed to do both. And there's also kind of neat circuits in here where you can set the phase differences between the legs so that you could pick your favorite gait pattern and have this thing run around, but then digitally reconfigure it as you go. And most importantly, living in this rat's nest of wires is basically a processor in memory. And so this is our first robot where you can actually write a program to it of what you want it to do, let it run around the world and carry out its task on the other end. And so finally getting into sense, think, and act. So the student that actually sort of did the back-end fab to turn this chip into a robot is Maya Lassiter, who is in my group. And of course, we had to put SmartBot on a 2020 penny to remind us of COVID, basically. Like the fact that this is its birth year, right? This is when it began. So what's cool about this robot is it's entirely programmed by light and it's entirely a computing system. And so Jung Ho actually did some very neat things, which was to write basically a user interface for this robot to lower the barrier for entry. And so if you want to talk to SmartBot, you turn on light, it wakes up and goes into a default mode. You flash light at it by just flashing light over the whole field of view. So you don't have to find this thing with a laser. You just flash light globally with your microscope and you write instructions to it. And then when you're done, off goes the robot doing whatever you want to do. And if you want to reset it, you can either write a new program by flashing new light, or you can turn the light off and the memory clears and you go back to start. In practice, the interface looks like this, which is super cool. There's basically a graphic user interface at the front end. You can pick what parameters you want this to do. You hit run. It'll flash the right sequence of light, and off it goes as a test chip that the Jung Ho did. And then you wind up, eventually the robot listens to you and locks into whatever pattern you demanded on the other side. All right, so for our case, we're going to talk about the electrokinetic propulsion version. And so the first sort of set of tests that we did was to validate that this works, that it swims, that we can control it and see what its kinematics look like. And so if you've got a robot that has 4 essentially electrodes that you can independently control with the microcontroller, there are 14 unique states that you have access to. There's 16 total, but 2 of those are all high and all low, and so unsurprisingly, those don't do anything. We went through all 14. We collected something like 60 experimental data runs on the different behaviors for this robot, and we were very pleased to see that we could span all the different degrees of freedom of this machine. So if you set, say, the 2 front high and the 2 back low, you get a nice forward drive state. You can also reverse it and you can go directly backwards. You can rotate that polarity by 90 degrees and then you can access slide states where you just move laterally across your body axis. You can set 3 high and 1 low and you get what we call an arcing state, which is sort of a superposition of turning and moving forward. And then you can set 3 low and 1 high and you get what's a turning state where you essentially pivot almost entirely in place. And so from a robotics perspective, this is great because you have control now over all of your degrees of freedom. You can rotate, you can translate, you can do combinations of the 2. And since you have a little microcontroller on board, you can also string them together to make sequences. So here we're telling this robot, go forward, then rotate 90 degrees, then slide along your axis and then turn. It's going to rotate. Now we're going to slide. And now we're gonna turn. Oh, no, it's gonna. And so, but all this is happening with the robot itself. There's no one telling this device what to do anymore. You write your instructions, open loop, off it goes doing stuff. Now, we don't want to stop an open loop. We actually want to close the loop. And that means we need to get sensors involved, right? We need something that's going to detect what's going on in the world around you. And so before we dove into doing robotics, we said it would probably make sense to validate the sensors actually work on this device. And so we wrote a very simple program, which is to measure the environment around you and then tell us what's going on by doing a little dance. And so the idea was this is a validation mechanism for the underlying sensing device for the robot. And so the way this works is we're going to tell our little robot to run around. It runs around for a bit, makes a temperature measurement, and then after it's made that measurement, you'll see it clocks forwards, clock backwards. That little step forwards and backwards, the phase difference between them encodes 1 bit of data. So it sends you back a Manchester encoded data stream of what it saw the environmental temperature to be. And so here's a robot sending you a 0. You can track the body displacement and then decode the message of what the robot wants to send. So 0, 0, 0, 0, 0, 0, 1, 0. You decode it by looking up a calibration table to 15.6 degrees. And then you check what the robot's reporting against, say, a thermocouple. And so we did a simple experiment where we took the robot in its Petri, we chilled it in a refrigerator, brought it back out, put it under the microscope, and let it passively warm up to room temperature. You record what you're getting from the probe. That's the open symbols. You record what the robot is telling you it's seeing. That's the closed symbols. And you get pretty good agreement. In fact, actually, when we characterized this, we found this is one of the better temperature sensors people have built. We get about under a degree, about a degree accuracy or something like that, but we're in a sub 1 millimeter form factor, which is actually quite cool. So not only do the sensors work, they're actually fairly good sensors for something, even though it's very tiny. And so now we were validated, and we said, cool, let's actually do something roboticsy, right? Let's do something where we say, look at our environment and carry out a task. And the first task we wanted to look at was thermotaxis, so basically trying to climb a temperature gradient or go down a temperature gradient. So make a measurement, see if it's hotter or colder, and then change your behavior so that you lock to the gradient you want to climb. We wrote a very simple version of this, and we picked these for experimental convenience. So this robot does one of two things. It either goes into an arcing state where it's both turning and moving forward, or it spins in place, so it does that spinning state. And it chooses between these two based on whether the temperature it just saw was hotter or colder than the previous temperature. And so the idea is that if nothing's changing, the robot will just sit there spinning around forever. But then when you change the environment around it, it'll suddenly go, oh, okay, I got to get out of here, switch into an arcing state and start swimming until it finds somewhere suitably cold. So a dead simple experimental verification. There's no way you're going to confuse something spinning in place from something moving, but still a way of getting some form of gradient climbing because the arcing state does move forward as you go. So here's our robot. We turn it on. We write the program to it. Starts up, boots up, and begins turning, looking good. Then Maya turns on Peltier pump underneath the robot. The robot goes, oh no, my world is cold, and then decides to go find somewhere warm. And now you start chasing the robot in your microscope, and so you have no idea what's going on in the movie. But afterwards, you stitch the data together by tracking the robot's center of mass in the microscope stage motion. You get graphs that look like this, where initially the robot is turning. It correctly switches into its arcing state until it leaves the edge of the Peltier pump and goes into a cooler zone, switches back into a turning mode. And then just to be good scientists, we actually flipped the gradient and then check that it indeed switches back into the arcing mode and goes off trying to find somewhere cool. Although it actually fails, the arc is a little too shallow and it doesn't quite make it over into the other zone. And so we terminated the experiment rather than let it wander around forever. So why is this cool? This is, in my opinion, awesome. I mean, you can debate of whether you need to do this or not, but I think this is the first microrobot that's fully autonomous. There's no human in the loop. We're not doing anything. Running its own program, making its own decisions based on data that it senses from the world. And so this is sort of a minimal sense-think act with no external overhead beyond the power source that the robot needs in order to function. We've recently gotten better at collecting data for this. So if you didn't like the microscope tracking, we rebuilt our experimental setup to collect over larger fields of view. And again, here's our microrobot. We wrote a slightly different program where you can switch between two arcing states, but it's the same general idea. If you're going into a gradient, you do one thing. If you're going away from a gradient, you do something else. And if you run these experiments, you get things like this, where your robot starts out going into the hotter environment. So it stays in one arcing pattern, making a nice circle. And then when it finally clears about 180 degrees, it sees, oh, okay, actually my environment's getting colder. And it looks like it does that diagonal motion. What it's actually doing is switching between the two arcing states. And so the time average behavior looks like a motion along an angle. And so you get nice trajectories that look like this. By the way, how am I doing on time? I have till 4:30?
We can go until 4:20, 4:25, and leave a little bit of time for questions.
Okay, that sounds great. So we can skip ahead.
I think we all want to hear as much as possible.
Okay, that's good. I'll briefly say this. I put this slide in for Sharon because I think you would find this cool. So we actually started modeling this, and we thought it was kind of neat. So we modeled it two ways, and I'll do this quickly. One is to do a very agent-based approach and basically say, okay, what does the robot do? It runs around, it makes a measurement, there's some noise in that measurement, you compare it against the program, and then you decide your next action. And if you run the agent-based model, you do get things that look an awful lot like the data. You get trajectories that have arcs, and they have these nice little linear trajectories on the other side. But we wanted to see if we could get more intuition out of this. Like agent-based models are cool, but are there more general things you could say, especially given the fact that the measurement process is inherently stochastic, right? It's a noisy measurement that you're making. So like what sets this angle? Like when will that happen? When will it not happen? And so we did something very physicsy. We decided to coarse grain this model and look at what happens to the probability that the robot has a given heading. And so the idea is the following, is that really what determines whether you see a high or a low for your next measurement is just the heading that you make into the gradient. Like the more aligned you are, the more probable you are to see something high. The less aligned you are, the more probable you are to see something low. And it turns out you can, if you work it out for a linear gradient, the only thing that matters is your angle, and you can show that exactly. Once you know that, you can write a very simple model by saying what I'm really interested in is the probability that the robot is in a particular heading state, given the fact that it randomly switches between arcing to the left or arcing to the right based on the measurement that it just made. And the leading order model that describes this is this very simple series of coupled differential equations where you have basically a rate of change of your probability of either arcing left or arcing right, coupled to sort of two drift terms that represent that arcing motion, a random walk term that represents uncertainty in the robot's ability to orient, and then these flipping probabilities that are basically your measurement, that if you measured the right thing, you might switch from arcing left to arcing right, but there's also a probability of error. This is a very classic model in the active matter community in biology. It's called the run and tumble model. And it allows you to import all of the tools originally developed for statistical physics to describe the configuration space of this robot. And I won't tell you all the details of how we got these, but some of the cool things you can say are the following: is you can analyze which programs are special and maximize the information transferred between the sensor to the robot. So you can make clean statements about how efficient is the measurement. You can show that if the robot moves slowly, it actually equilibrates to a Gibbs distribution. So yeah, I thought that's what was there for you. Yeah, it actually satisfies detailed balance. It's very cool. So you get a Gibbs distribution, which means that you can build effective temperatures and energies for the robot's behavior, again, by choosing the program that it executes. And my favorite is this result, that your uncertainty in your heading, so like the width of the bell curve of heading positions and the rate at which you can change it, your velocity of updating that heading, are constrained, and they satisfy an uncertainty relation. So the uncertainty, basically the variance of one times the variance of other, always has to be bigger than that random term on the other side of it. And that one holds regardless of the program that you write. So you can either be fast, you can be precise, but you can't be both. There's an inherent trade-off in this design between those two parts. And so it's kind of a fun little thing that we've been writing up to. It's a pure theory statement about general statements that you can write about this, regardless of how you program it. Just if this is the sensor architecture you have and this is the task you're doing, there's some things you just can and you can't do. All right, so the last thing I will tell you about briefly is what are these for, right? What are we going to use them for? And our group has a lot of different answers to that question. Some of it is in nanomanufacturing. Some of it is unrelated to robotics. We have a project in doing deep sea carbon monitoring. We have some projects in other spaces. We have a project that we're starting in dentistry, which I think will be very fun. Yeah, it's cool. We're going to do anyway. But there's sort of a broad question in microrobotics about what are these things good for? And I think that most people dive straight into this, right? This movie, Fantastic Voyage of, we're going to miniaturize ourselves and go inside of a person and do medicine. I'm not a huge fan of this movie. I personally don't. I think it's okay. I think it's pretty good. I think it's like a little wonky in places. We'll talk later. But B, I'm a little skeptical about this claim sometimes, is I think that often there are things that you could probably just do with other medical procedures. And so one of the questions our group really tries to answer is like, when do you really need a microrobot in precision medicine, right? And we're not gonna do this anytime soon, like it'll be way in the future. But like, when is there a task where just the problem definition would inherently require a robot? And I think it's a hard question to answer. You basically need something that has to be small, has to be mechanical, like you couldn't just do it with drugs, and it has to be precise or controlled, right? And that's kind of a weird axis to go on, especially if you're in the medical space. Like things you usually care about don't necessarily have to be that small. And so one that we've identified that we really like is this very like blue sky project, which will probably take me the rest of my career, but I still think it's worth doing. which started when I came to Penn, and I met with my now collaborator, Casey Cullen, in neurosurgery, and he pitched this idea to me that we've been working on since then. So Casey's group works on peripheral nerve injury, and Casey told me this interesting story that in the US, there's something like 100,000 nerve injuries, and even in surgical intervention, about half of them end in failure. So 50% of the time, you can restore some limited capacity for sensory or motor function, but 50% of the time you can't. And the typical demarcation between these is just distance. It's how far is the part where the nerve is severed from where it actually needs to be. If the distance is like really far, like if you're supposed to be connected to your fingertip and you sever the nerve here, there's not really obviously going to be a surgical intervention that will do that. That's a meter in length. But if it's shorter, surgeons have tools that they can employ, like they can put little guidance tubes in to try to show the nerve where to grow, and the nerve will try to regrow back to that muscle target and reconnect. Now, the challenge is if the issue is fundamentally distance, what it really means is it's also partly time, right? You have to get to the muscle target before the muscle dies or before the regenerative conditions fade. And so what you desperately like to do to improve these odds is figure out a way to make nerves grow faster, right? If you could just get them to move quicker and show them where to go, then you'd have a better chance of having a positive patient outcome. In most of the technologies that get used for peripheral nerve repair don't do this. They're largely built around guidance about showing a nerve where to go or grafting a nerve back into place to make the connection. But none of those things actually accelerate the process. Now, there is one interesting way that you can make nerves grow faster, which is you can stretch them. And it's a process that they have that's really tied to how they become meters in length in the first place. So basically, they wire when you're an embryo, and then you stretch on them as you grow. And so in order to keep up with your body growing over the 20 years that you do, they always retain this ability to be grown about 10-fold faster when you put mechanical tension on them. What's interesting is that this robot and this bundle of axons is not super far off in scale between these two sides. And likewise, if you asked how much force do you actually have to apply to trigger that stress growth mechanism, it's about a nanonewton, which you'll recall is exactly the force output of that robot. And so Casey and I got interested in this idea is, could we build microrobots that literally pull nerves to where they need to go? Like, could you build one that's surgically implanted in a tube in the same way that we build guidance tubes, but now instead of just passively letting the nerve grow, you try to tow it back to the other side, and then the surgeon would say, remove the microrobot, remove the tube, and hopefully accelerate that process of regrowth. Now, this is obviously super hard. This is like moonshot hard. It's going to take us a long time. But we've been having fun sort of doing the first steps. And so after maybe about a year or so of work, we figured out how to get these things not to kill each other, which is great, a major accomplishment. So believe it or not, cells don't like robots. Robots don't like cells. Not a surprise here. But this is a cell culture of what are called dorsal root ganglia. They're essentially growing their axons outward. We're using them as a proxy to represent peripheral nerve injury in our petri dish before you do anything else. And you can see we have two robots hanging out in here. And after some time, you see the robots start moving around as the axons start to bond to the backs of their bodies. And we played a lot of tricks here to coat the robots in chemicals to make them attractive to the axons, to build the robots out of materials that don't get murdered by the axons. All kinds of fun research went into this. In the end, you wind up with cool images like this, where you have your robot and now axons have bonded to it on the top. And then your postdoc goes in and tries to get the thing to move. And lo and behold, the locomotion of robots through axon bundles is an unsolved problem in robotics. So we're super stoked on this data set anyway, though. And I think it's really cool, right? This robot was co-cultured with these cells for like 10 days. It's not dead. In fact, it's actually moving quite well if you look at its front actuators. And it would love to be able to pull these axons that are tied to the back of it. We just don't know how to engineer that system yet. And so this is a really fun challenge, but I think it's equally exciting, right? That there's legitimately a path to doing at least some of the first steps towards this. And I think it's a super exciting robotics problem. Like, how do you do mechanobiology with a robot, right? Like, how do you pull on something and control it with this machine on the other side? And so I'll give you kind of the broad pitch of kind of where one of the things I think is super cool, and I'll explain what I mean in a second, and this will be my last slide. This is sort of the story I tell our group members when they come in and our vision of what we're trying to do. And it's the statement at the bottom is I really think this is correct, is we're entering an age where the micro world is no longer the privileged domain of biology. And what I mean by that is if you were to look under a microscope 40 years ago, right, and you saw something moving around and doing stuff, it would be alive. There was nothing humans would build that would be that, right? Or if you looked under a microscope and there was a system, right, that was doing something, it would be alive, right? There weren't systems that we knew how to build at that scale. What's super cool and what's changed in the last 20 years is that that's no longer true, right? We can start to build systems at this scale where we can exert forces on things that are very tiny. We can build systems for measurement at this scale and report what biology is doing. We have new windows to sort of go into this dimension and not just watch it like we do from microscopes, but interact with it, but stimulate it, but control it, but push and pull it. And it's going to take decades to get it to the point where it's like that rotifer on the slide. But I personally am super excited to be at the start and to get to build out this infrastructure into this being a domain that humans can shape and engineer and control. So that's my talk. Thank you. I'm happy to answer questions for anybody, and I'm done.
Questions for our speaker?
Yes.
Are all the robots moving in liquid?
Fun question. So all of these, yes, although there is a project. So we did build a family of actuators that are designed to go in air. And so it's a polymer-based actuator where we basically put the electrolyte inside of it and it's all closed up. And that works really well. Like we've built test structures of it where we can manipulate it in air and drive it at the voltages we need. The postdoc working on it was working on integrating it with the electronics and then got poached by industry. And has a great job at a startup where he makes more money than I do probably. But I think, so right now, yeah, they all live in water, but one of the secret goals of the group is to have microrobots in any environment that you can have. And so one of the things I didn't tell you is these guys do really well in fresh water. These guys do really well in salt water. The trade-off where this becomes a bad design and this becomes a good design is actually pretty clean. There's about a very specific conductivity where you switch from one to the other. And the stretch bot that I showed you at the end, that one's engineered for tissue. It's slower than the others, but it outputs more force. And it doesn't get biofouled, which is also really important, right? It can't die. And so one of the goals is we like designing new actuators for different environments. And the two we want to do are terrestrial robots, so coming out of the water and moving around on land. The trade-off is you need more force because the ground is adhesive, right? There's lots of surface energy to that. So you need big, beefy actuators, but that makes you slow. And so you have to engineer around that as best you can. We also want ones that can fly, and we have really crazy ideas on how to do that and no data whatsoever. But that's another goal for the group is figuring out how do you do flight at this scale. And then, you've got land, sea, and air, and you have a little micro-robot kingdom that you can, you can play with. Thank you.
What drives a micro-robot in the last project?
What powers this one?
Yeah.
Yeah, it's interesting. So this one is still optically powered. And, for the particular application of PNI, in a lot of cases, that's okay. A lot of the injuries that are treatable are like kitchen accidents or something like that, and they're in the upper few millimeters of the tissue. And if you look at how far IR penetrates, you can actually power this robot. There is another project that if the NSF ever gives money to anyone again, we'll maybe get to do it. Where we're looking at doing sort of magnetic power transfer techniques, both as a way of powering the onboard electronics and then also as a mechanism of locomotion. And so that's sort of the plan if you want to go like deep in the body, right? Or if you want to go deep in some environment that you can't see. But the beautiful thing about electronics, right, is they're hot swappable. So if you want to go in one environment, you use power source A. You want to go in another environment, you use power source B. And right now, these are all optical.
So this has to be guided. You should be able to see the micro-robot in order to program your.
This one, yes, but the smart one, no, right? Like this robot here is, you just have to see it initially and then, or like it has to be somewhere in the field of view. So the other big plus, right, of having onboard electronics is you don't have to track it. You can just know, like, as long as I get enough power, it's going to do what I told it to do. It's like having a Wi-Fi signal or something like that. I don't have to know where the router is. I just have to be able to see the signal on the other side. I think Cam, and then I don't know who.
Sure. For the one further along that's pulling the nerve cells around, can you speak to the material changes that you mentioned that you had to do some to make the cells stick to it?
Yeah. So it's like so the first change you have to do is get rid of those beautiful platinum actuators. so they don't work, right? And they don't work for two reasons. And one of them we kind of knew, like the force output is just barely enough, but then that would be if there were no tissue in the way at all, like if you're just moving through water. And so long term, that's not viable. You need actually probably about a micronewton of force to move through like a tissue model at least. So you have to beef up the force scale, and that motivated one choice. The other is that you can't biofoul, right? You have to be able to operate without the surface getting coated. And if your actuation mechanism is ions absorbing the platinum, you can also have proteins absorb the platinum, and then you're screwed. And so we actually tested 4 different classes of actuators, and that was kind of part of the first work that we did. Is Casey gave us cell cultures. We cultured them with the actuators, and then we would check on them every couple days and see like who's dead, who's doing well, like what's going on. And the ones that work well are these polymer-based actuators, so things based on pegged ionic liquids and PEDOT-PSS. And then you play some special tricks with heat treating it to get the reliability up to where you could carry out your mission. Sure, I think, yeah.
Yes. So basically, like, how fast can those voltage-controlled actuators switch?
Oh yeah, so the C's, the first ones.
Yeah.
It's pretty cool. So there's 2 ways to answer that question, right? Is how quickly can you adsorb the ions, and then how quickly can they move through the fluid? We don't know the answer to the first one because the second one's the limiter. So basically what you see is if you step from, you give it, actually I have the data set in another slide show, I'm happy to show it to you, but like if you step a voltage from high to low, you get an exponential relaxation. That's just, it's set by the force balance between the elasticity of this bending structure and the drag in the fluid. And they're computable, like you can actually calculate the solution analytically, and if you just calculate it and you fit, you get parameters that match for platinum, so that's all good. Those numbers work out to somewhere between a millisecond to 100 milliseconds, depending on the aspect ratio of the structure. And so what we typically see is we can get up to at least a millisecond or 10 milliseconds, depending on what we want to put. Basically, wider things do better than long floppy things. We have never been able to make it short enough to where we could establish the upper bound from the reaction kinetics. And so you can basically go down to like, a 1 micron structure and like you're trying to drive it and you still don't see any cutoff on the other end. So the short answer is basically somewhere on the order of a millisecond, which is pretty good, right? There's not much that goes on at 100 microns that's faster than a millisecond anyway. Like diffusion's not faster. Most things can't move mechanically faster than that. And so we're happy with it. But there is still this like engineering side of like, yeah, but what, like that's the.
Like a self-powered, like an ultrasound powered.
So yeah, so that's again tied into this thing that the NSF is, or I guess Trump is holding hostage. So we wrote this proposal about how to do power transfer to do basically magnetic assisted power transfer for acoustic style propulsion. And there was this trick where if you do it the right way, you can also integrate that with electronic control. And I was really excited about this proposal, and I wrote it as my career award. And I was like, you're going to swim at like 1 millimeter per second, like 10 centimeters deep and whatever. And like you could still be controlled with electronics. I think it's a really cool idea. And maybe one day I'll get to answer that question for you. Yeah.
Can you speak to the tunability of the output force? Like obviously, you would have to scale these up, but in applications for other biological samples,
Yeah.
it'd still be usable at larger scales.
No, actually, so there's 2 questions, right? One is can you scale up to larger scales, and the other is what's the general sort of scaling of these things? And the different actuators have different scaling laws depending on the mechanism, right? So for C's, because it's a surface-driven process, there's just an intrinsic force scale that you get. It's basically the surface tension times the thickness. And so if you modulate the thickness, you can make that higher or lower, but there's not that much range that you have because as you make it thicker, the stroke gets smaller too. So there's a trade-off. It's similar for the swelling style actuators like polymer ones, but it's not as bad because that's a volumetric process. So Michael Reynolds, the postdoc that was in there, and I wrote a whole paper about this where he basically compared all of the electronically controllable actuators for microrobots. So piezos, thermally driven actuators, polymer-based actuators, Cs, et cetera, and plotted sort of their trade-offs of like response time versus stroke distance, response time versus power, et cetera. And they all sort of have inherent trade-offs where there's some power law that makes you worse as you go bigger. And sort of the interpretation we had is that like a scaling law runs both ways. It says that as you go small, you tend to win out, and as you go big, you tend to get worse. In the same way, like inertia is really, really great when you're large, but it drops out from under you relative to viscous forces when you're small. And so kind of the way our group sees it is like, there are some actuators where they're just meant for things that are being small, and there are other actuators that are meant for things that are big. These are small actuators. They will always be bad for big stuff, right? The properties that make them competitive at small, like the scalings that they have with length, are all favorable for being tiny. And as you go up in sizes, they get worse. intriguingly, the crossover for almost all these things is about 1 millimeter. And so there's kind of a nice, intuitive part to that where it's like, okay, if you think paramecium, you think ant, very different morphologies, very different ways of moving. And if you look at a lot of the scaling laws for the basic physics, most of them cross at about 1 millimeter, right? That's where like gravity beats out surface tension. It's where, inertia beats out, viscous forces. It's all right about at that one length scale. So my advice would be, we do know scaling. I'm happy to share it with you. And from an engineering side, you can cheat to make forces bigger or smaller, but you really don't want to go up by like 3 orders of magnitude because this will lose, right? It'll be a bad design choice. Yeah.
You talked about like gathering information from your environment. I'm curious about like communicating information between the different robots. Like what are the difficulties associated with like communication and what's like the progress?
Yeah, so that's the ongoing collaboration with David's group. That's our next chip, right? And where you really want to go is swarms, right? You want to have like if you're tiny and you're not smart, the way you get around that is you talk to your neighbors and you work together. And so sort of the next chip that their group has designed and taped out has a communication modality where like you can raise and lower the voltages on your electrodes to create an electric field that you're modulating in time. And then other robots can use their electric field sensors to detect that and receive data. And so, David can probably speak a lot more to the circuit side of it, but the robotics side is, we wanted something local. We wanted, you to be able to exchange data between your neighbors. And that kind of fits the bill, right? It's a local communication modality, it's digital, et cetera. The other thing that they did, which was super cool, is the robots have names. So you can do things where you can say like, I'm sending the signal, if your 4th bit is 1, then you should listen. If it's not, ignore me. And so the idea there was like, again, if you want swarms, you maybe want types, right? Workers and drones and whatever. And so you can write in as part of your program, like, no, I want you to go do this and you to go do that. And if you see this thing in your environment, I want you to switch to like this other behavior. And so long term, that's really where we want to go, right? You don't want to spend your whole life just being one tiny dumb robot. You need, biology tells you that's not how it works. You don't want one cell, you want billions of cells, right? That's how you do something interesting.
We're about at time. Let's give Mark another round of applause.